Hi, welcome back. In the last few videos, we've encountered equations that have looked like this, where we have r is equal to some function of theta on the right-hand side. And what I'd like to do is I'd like to spend a little bit of time talking about what this means and how you would plot such a equation in polar coordinates. So, we saw this equation, so let's start with a new equation. So r is equal to 1 plus cosine of theta. And so in both of these examples, what I'm doing is I'm writing r is equal to some function of theta. And I'm thinking of these in polar coordinates. So when you see an expression that looks like this, what we're doing is we're starting off with some angle, theta, and then depending on what the angle is, this has the input, then the output is this function of theta is equal to r. This is our output. And so what we're doing is we're taking our angle as the independent variable, and then the dependent variable is what the radius is. And so what it's saying is for different values of theta, we have some distance r that corresponds to it in the picture. So for different points, for different angles, we plug in an angle into this function, and that's going to give us what the radius is that corresponds to that. So in words, what we're seeing is that we allow theta to vary on its domain, which this domain is often hidden and often is a multiple of 2 pi. We allow theta to vary on its domain, and the output, f of theta, corresponds to the radius from the origin, from that for a point with that angle. And so, for example, for our function r is equal to 1 plus cosine of theta, what that's saying is I want to plug in theta, not r. So, for example, I plug in theta is equal to 0. R is equal to 1 plus cosine of theta. Cosine of 0 is 1, so I get r is equal to 2. If I choose theta is equal to pi over 4, then cosine of theta is root 2 over 2, and I get 1 plus root 2 over 2. If theta is equal to pi over 2, then r is equal to, cosine of theta is equal to 0, so I get 1. If I have 3 pi over 4, and I plug in cosine of theta, I get negative root 2 over 2, so 1 minus root 2 over 2, and when I plug in pi, I get 0. And so what this is doing is, for different values of theta that I plug into this equation, I get different values of r that correspond. So now how do we plot this graph? So now what we'd like to do is we'd like to plot r is equal to 1 plus cosine theta. So I think that when you're getting used to doing this, what it's really helpful to do first is to plot these functions first in Cartesian coordinates. Cartesian. So as a Cartesian function, or Cartesian graph of a Cartesian function, what we're seeing here is that we're just going to look at this as r. This is going to be the r-axis, and this is going to be the theta-axis. And so when we look at 1 plus cosine of theta, that takes our normal cosine function and it raises it 1 unit. And so what we get is we get a function that does this. Right, and so at 0, we're at 2. At pi over 2, we're at 1. At pi, we're at 0. At 3 pi over 2, we're back at 1. And at 2 pi, we're back at positive 2. So this is plotting r plus cosine of theta as a Cartesian function. But what we'd like to do is we'd like to plot it as a polar function. And so instead of thinking this 0, 2 as a point where we're at 0x and 2y, we need to think of it as a point where we are at angle 0 but radius 2. All right, so this point is the point 0, 2, or sorry, r comma theta, 2 comma 0, where r is 2 and theta is 0. And now we're going to go and talk about the next point, which is pi over 4. So this is the angle pi over 4. And we want to go 1.4 in this direction. So this is 1.41, comma, wait, that's not what I want, sorry. 1.7, 1.707, 1.7 in the radius direction at an angle of pi over 4. And let me put in one more point and then I'll talk about it. So this point right here is angle is pi over 2 and the distance is 1. And so as we connect these points, what we see is we are tracing out this part of our Cartesian function. We're starting at a distance of 2 from the origin, and we're ending up at a distance 1 from the origin. So we're starting at a distance 2 from the origin. We're ending up at a distance 1 from the origin. And so as we come in here, this radius is slowly decreasing from 2 down to 1. All right, let's do this again, but on the next part. So now, instead of plotting the points, what I'm going to do is I'm going to do this heuristic idea that says I'm starting out, when I'm at pi over 2, I'm at distance 1 away from the origin. But when I get down here to angle pi, then my distance to the origin has to be 0. So as I come down here, my distance goes from 1, and when I get down here, when I'm at distance at pi, as I rotate my angle through all the possible angles, then my angle, the distance from the origin, gets down to 0. Now if we go back up the next direction, here, this now starts off at 0 and increases to 1 as my angles get bigger. And then the last bit here, from 3 pi over 2 to 2 pi, follows this same idea, starting out at distance 1 from the origin and ending up at distance 2 from the origin. All right, and so our picture, instead of having horizontal and vertical lines, because that's what you get in a Cartesian coordinate system, what we have now are we have these diagonals from the origin that are telling us, well, how far along these diagonals do we need to be. All right, so how do we know when to stop? How do we know when to stop drawing? So in this case, we see that when we are at 2 pi along this, in the Cartesian function, we see that the function repeats. We see that the period of our function, r is equal to 1 plus cosine of theta, is 2 pi. And since the period is 2 pi, then we only need to sweep out 2 pi. We only need to graph 2 pi for theta. We only need to go from theta is equal to 0 to 2 pi. If the period is not 2 pi, then we need to get the least common multiple of the period and 2 pi. And here I'm being rather sloppy, because least common multiple normally only works for integers. But let me just give you an example. So let's say the period of our function, let's say I'm dealing with r is equal to cosine of 4 pi over 3 theta. Is that what I want? Or maybe I want 4/3 theta. That's what I really wanted. So cosine of 4/3 theta allows theta to go like this. What's the period of this? Normally cosine has a period of 2 pi, but because we multiplied the theta by 4/3, it's going to get to that period 4/3 as fast. So the period here is 3/4 of pi, 3 pi over 4. Or, I mean, we want it to be 2 pi, so 3/4 of 2 pi. That's what I want to say. So what we're seeing here is that this function is going to repeat every 3 pi over 2. Now the thing is that once we get to 3 pi over 2 and we get back to maybe the 2 pi, we're at a different place than when we started at angle 0. So the points we have to plot are going to be at a different place, and it's not like we're going back over the same curve again and again. What we need to do is we need to figure out where down the line do we get to this same point again. So here we are at 3 pi over 2. The next time we come back to the period is at 6 pi over 2, which is 3 pi. The next time we get back to the period is 9 pi over 2. And then the next time we get back to the period is at 12 pi over 2, which is 6 pi, which is a multiple of 2 pi. And so what this is saying is that to draw the whole graph of r is equal to f of theta, we need theta. We need to use domain theta goes between 0 and 6 pi. All right, in the next videos, we're going to put these into the computer and draw these pictures and see what they look like. And we'll see this need to use this larger domain for that reason. All right, I'll see you shortly.